Okay, so let's get started again. So this session will cover like two tutorials kind of thing. One to start with the MVAPitch one. The first will be presented by Nat and Ben. So Nat is actually a software engineer. He's working on the MVAPitch project for several years. So whatever the code and all you see is the primary developer there, working with a lot of other students, staff. Um, so his current development work includes high-performance interconnects, parallel computing, scalable startup mechanisms, and performance analysis and debugging of the MapIts library. And he will be joined here with Ben. He's a PhD candidate at the Ohio State University, and his research includes high-performance computing, parallel architectures, network-based computing for HPC, security, and parallel programming environments. So specifically, he's interested in efficient offloading, parallel programming models, and computational workloads to smart network cards like the NVIDIA's Bluefield DPUs. And he also contributes very actively to the MAPI software and also the OpenSWAM standard. So with this, let's welcome Nat and Ben. And I think we have around 45 minutes, so we can make it interactive, ask any questions you might have on the MAPI, so they know ins and outs, so they should be able to explain it much more in detail. Okay? Go ahead.
All right. Thank you, Dr. Panda. Yeah, like Dr. Panda said, please feel free to jump in anytime, ask questions. We'll just keep moving other than that. So I think everyone is probably familiar with MVAPitch since you are at the MVAPitch User Group Conference. But we are celebrating 25 years this year with a long history of innovation and developments in the HPC field. For anyone that is not familiar, we have built a large integrated top-to-bottom environment around the MVAPitch software stack that includes both our primary focus of MPI, but has also expanded out into PGAS, OpenSHMEM, hybrid models, and then on top of the MPI layer, we've been building into other domains like AI, big data, and whatever we can try and use MPI to empower. For in terms of your user experience, we have recently updated all of our documentation, moved them all into read the docs that should be a little bit more easily searchable. So we would encourage you to all take a look at that to find the instructions for latest installation, guidelines, documentation for all of the tuning parameters that we're going to go over, and really more details on anything that we're going to talk about today. Other than that, we do have our discuss and help mailing list, so please reach out at any time. We're always more than happy to help everyone out. So some stuff we're going to be going over today. Ben's going to take you guys through some CPU process mapping parameters, which is kind of a first level design that first level optimization that we recommend everyone start to look at when they're optimizing their application performance, as well as some of the main network fabrics that we use in the MVAPitch library. Then I'll go over a couple of the advanced features in MVAPitch Plus, and then we'll kind of bring that all together with a case study at the end. So with that, I'm going to turn it over to Ben.
Thanks, Nat. So I presume everyone here is at least familiar with some level of job launching, just given that we've been using MPI for who knows how long at this point. In most cases, we tend to recommend using Hydra. It's a parallel job launcher that's been associated with MPitch and MVAPitch, and it's pretty much cluster agnostic. So on any cluster you build with this, you can just run out of the box. Certain clusters may also have PMI interface for exascale included, and we've noticed in a couple of cases that may conflict with Hydra's PMI1 compliance. So we just have a simple variable MVP PMI version set to PMI1. I'll take care of any sort of these bugs for mainly scale out transfers. The other one, because just given that most clusters, at least that most people use, end up using Slurm. as opposed to say Torque or other job schedulers. This is mutually exclusive. You configure MBAPIC with this. You don't get MPI run, MPI exec, and the Hydra compatibility. That's pretty much it in terms of job launchers. Everything else in the next subsections kind of follow through accordingly. So first off, one thing that most people eventually realize after running their applications a few times is, if you really want to fine-tune your process mapping rather defines kind of what you need in terms of either want something latency bound or something that's more bandwidth bound. So there are technically four common cases. So we have bunch, scatter, spread, and custom mappings. Depending on what job launcher you use, you may have to set certain variables to see, okay, is a given MPI rank or process being mapped to the physical CPU core, NUMA region, et cetera, that you wanted it to be placed on. And so for Hydra, that's Hydra topo debug equals 1. Otherwise, you can set Slurm's binding verbosity to its maximum to verbose, so on and so forth. Our first case is bunch mapping. This is really good. This is primarily good for like say optimal intranode shared memory transports, because in that case you're binding every process in a linear fashion. So rank 0 maps to physical core 0, rank 1 maps to physical core 1, so on and so forth. And this allows you to get maximum performance from intranode communications such as Linux CMA or XPMan. This is not necessarily the best for resource distribution if you're using a hybrid environment of say MPI plus threads. And as I mentioned before, here these two bottom spots are how you would do bunch mapping for using the Hydra launcher and then using Slurm's SRun launcher. The Slurm has some interesting setup for round robin and block based mapping. So in this case, you have to specify block : block for your distribution, not just CPU bind equals core. For scatter mapping, you have a similar story. In this case, this is really good if you want to say initially test if you have like say a small number of MPI ranks per node, especially because then you end up more likely placing yourself closer to say network resources, for example. Not the best for intranode transfers because at a certain point you may have to cross say multiple sockets or multiple NUMA regions if you're trying to look at intranode latency. This is otherwise with the Hydra launcher is usually defined as just you're mapping by sockets as opposed to say mapping by NUMA. Only one of those can be done at any given time. And then in a similar case for SRun, instead of doing like bunch column bunch or colon bunch, you have to just place them with cyclic, and that does the same round robin process placement. For spread mapping, this is kind of the best of both worlds. This requires a bit more intuition, depending on how many processes you have per compute node, and then how many say threads, for example, you're requesting, say for example through OpenMP, and that just requires more of a defined mapping of say for Hydra map by core, how many CPUs you want divided, how many CPUs are you using divided by the process per node count, and you have a very analogous case for Slurm. This also kind of just works in general across the board in terms of optimal process placement. For those who are familiar with the older MBAPIC 2 software, similar functionality and performance can be gained doing the same thing with later versions as well. This kind of gets you to the point of there's no one mapping that fits every single problem. If you need something more latency bound, that's like latency critical for say, and you're running on one node, your bunch mapping is going to get you the best case spread. But what if you need something more fine-grained? You can do some mapping. You can do a bunch of mappings via Slurm or SRun configurations, and their own documentation is full of very nifty ideas. With Hydra, by comparison, you have binding across a whole slew of architectural components. So you can actually go down all the way to like binding per network device if you want to do some interesting experimental configurations, as well as user-defined process mappings. Any questions on this part before I get into the network modules? Okay, cool. So for those who are familiar with this from last year, this will be a good refresher. So for the most part, MBAPIC these days has has two, or follows the CH4 device, the CH4 module set that was provided by MPitch 3.4 starting in 2021. This comes broadly into two network modules, as they're called. Given the sort of like dissolving, quote unquote, of the OpenIB Open Fabrics framework into UCX at the UCX camp and OFI camps, so to speak. Broadly, we recommend UCX on any sort of InfiniBand or Rocky specific network, and older versions of OmniPath will also be compliant with UCX, given that initially was an InfiniBand in a sort of InfiniBand derivative and enhancement. And then Open Fabrics we kind of recommend for anything else. So modern day Open Fabric, modern day OmniPath Express, Amazon EFA, HPE Slingshot, so on and so forth. Like those networks will benefit better from OFI performance, given that the vendors that work on these interconnects contribute heavily, and I really mean heavily if you look at the commit history, to the OFI stack. In particular, and then we also have our own shared memory modules for either regular intranode transfer or, let's say, GPU or IPC. For UCX, it's fairly straightforward. Either if you want, if you're going to use a particular UCX, you can end up using the embedded module that comes with MBAPitch, or specify a specific path. And then here's some common variables, either for your eager rendezvous threshold switch off, how many rails, meaning how many network adapters and ports per adapter basically are using. UCX currently has a maximum support of 4 for your eager transfers and your rendezvous transfers individually. Also transport layer services. So this includes your Q pair types, your Q pair or endpoint types. So from RC, UD, shared memory, etc. How many devices you'll use, and then debugging log for the sysadmins and everyone's groups. Similarly, for OFI, it's the same process. Just instead of either embedded option or some pre-configured option. Usually this one ends up being useful in certain clusters where you have a proprietary lib fabric installation, i.e. Slingshot for the most part, although they have recently upstreamed their stuff into the open source lib fabric. We have a couple of variables here as well. For the most part, these are just good for either fine tuning or network experimentation, given that MBAPitch will Given that MBAPitch will try to choose the best provider or best network configuration through OFI for your work. And then lastly, enable HMAN that allows OFI to actually use GPU direct RDMA features that were sort of mentioned on and off in the talks from this morning. It's very provider dependent. Before I hand it off to Nat to discuss dynamic tuning and GPU awareness, any questions on this part? I realize I kind of blew through it quickly.
One question. So sometimes UCX is buggy. Like we feel like UCX is not behaving in a performant manner. Do you have an interface where we can disable UCX and use your legacy mechanism?
So if you wanted to go outside of UCX, then we would recommend just an OFI build. There is verb support in OFI, and something we have worked on in the past is optimizing the verbs provider. We're not currently shipping that because we're still working on it, but the verbs provider tends to be comparable, but slightly worse at large scale than UCX is typically what we see.
So this will be a complete new build, not like an environment variable to turn on and off.
We can provide versions that have support for both netmods. The issue is it will make the UCX netmod function incorrectly. So it will work on some applications, but you'll see even more buggy performance because UCX doesn't play nice with others. Okay, so any other questions on that? All right, so since we've covered the basics, so everything Ben just talked about is available in both MBAPitch and MBAPitch Plus. So in our open source version and our enhanced version that's available as a binary. The stuff I'm going to go into now is specific to MBAPitch Plus, which is our binary only version. And these are some of the advanced features that we've been working on lately to really boost performance. So the first is our dynamic collective tuning. So we started this project about a year and a half ago when we released InVapich Plus 4.1, and this enables on-the-fly collective selection tuning. So for any given collective, there are a variety of algorithms that can be used to actually accomplish that communication pattern. And all of those algorithms have different advantages and disadvantages. In general, we typically find that some algorithms are good for large messages, some are good for small, some are good for medium. But the specific one, right, you may have 2 or 3 collective algorithms that are good for small messages, but the threshold where you're going to transition is highly system dependent, it's highly network dependent, and sometimes it can just be a little bit of a toss-up on which algorithm is going to perform best at any given message range. So the idea behind this dynamic tuning framework is to take the knowledge we already have of those couple of algorithms that perform very well for a given situation, and then test them on the fly while your application is running. Because in a long application run, the first few iterations can functionally act as warm-ups. We don't really care if they're slightly less performant if the rest of the application run is the best case. So what this does is essentially run multiple different algorithms and try to identify which is best for your particular workload. We've seen a lot of success with this. We can get a much smoother performance curve at the micro benchmark level. And we've seen anywhere from slight to significant speed up on application tests with no particular loss in performance compared to our older static tuning. So the nice thing about this is, as a user, we've provided a bunch of levers that you can use to customize your experience with this. So the most important one is enabling the dynamic tuning. Now, this specifically enables whether or not we're going to continue to actively retune during the application. So these are all through the MPI CBAR interface, which is standard compliance. If you look at the MPI standard, you can see exactly how to interact with these in an application. But in an optimal scenario, you would run a few iterations first as a sort of warm-up to get that data collection. Then you would disable the tuning, so it would freeze your tuning tables in place as they are, and then you would have an optimal run for the rest of it. If you don't do that, at a certain point, and that's what this threshold, the dynamic tune threshold is, we're going to retest to make sure that we're still getting the best performance. Circumstances might have changed. There might be more network congestion. Who knows? Your nodes might be shared. The intranode links can be more busy. Hard to say. If you want to disable this entirely, we can force back to the static tuning tables, which is very useful for testing the impact it has on your application. And then the other sort of hyperparameters we have for this is the test count, which is how many times we'll test an algorithm. In general, we find that keeping this low is usually fine. It minimizes the warm-up requirement of the framework. And then the really interesting ones to play with are the local evaluation metric and the selection metric. So the local evaluation metric is going to be how a process determines what it thinks is the best algorithm. So whether it is the average latency of all of the calls to that algorithm, the minimum latency, or the lowest maximum latency. Similar concept with the selection metric. We're going to look in the aggregate over all the ranks on that communicator, which one had, so typically we try to minimize the maximum average latency. So that would be try to have the lowest tail latency on your collective. So these can be interesting to mess around with and see how they impact performance on your system. And similar to what Ben was talking about with the process binding, there's no one right answer here. These can be a little bit non-deterministic in terms of what is best for a given application workload. All right, any questions on that before I move on? All right. So GPU support. So again, this is going to be specific to the designs in InVapich Plus. Our regular open source InVapich has the basic level of GPU support that is provided by the underlying MPitch implementation, which is acceptable if you just want things to run, but it is not particularly performant. So the big concept in GPU enabled MPI is to essentially offload everything that the user would need to do. So if we look at a normal, and we're going to use CUDA as the example here, but if we look at a normal workflow with MPI and GPUs, we need to take data off of the GPU, move it into the CPU memory, then we need to perform a send through the network, and then on the receiver side, we're going to resend it, receive it from the sender, and then copy it back to our GPU. This is pretty straightforward. It works. It will get the job done. And it's very easy for a user to program, but the performance is not very good. CUDA memcopy is not a particularly fast operation, and we have so many more technologies now that we would like to take advantage of. So, an advanced user might handle this themselves by essentially pipelining the process. So pipelining the copies from the CPU from the GPU to the CPU, then sending, performing non-blocking sends, and then on the receiver side, doing this in reverse, performing non-blocking receives with an async mem copy back to the GPU. And this would be very, very efficient, but it's a pain for anyone to program into their application and requires you to change your application code, which nobody likes doing. So the idea for GPU-aware MPI is to handle this all within the library. So we just do an MPI send and an MPI receive, and we'll handle whatever the best way to get your data from the GPU to the receiver node's GPU. We can do this in all sorts of different ways. We're not going to go into all of them right now, but this essentially takes all of that workload off of the user's plate and is handled inside the library. And it takes advantage of the fact that because we have a variety of methods available inside of MPitch, we can hopefully choose the best one for your particular data movement case. So this is great because a user does not have to change their code at all, and they still get all the performance benefits. So this is from very early on in our performance optimizations for MPitch Plus 4.1, but this shows the performance gains that we get from integrating the GDR copy designs. We've had GDR copy available for a very, very long time, but this was as we were going through the process of re-implementing it in MPitch Plus. And as you can see, we get a very significant latency reduction, especially for small messages. One of the major features that differentiates MPitch Plus from other GPU-aware MPI libraries is the availability of on-the-fly compression, which allows us to compress GPU data as a part of the MPI send and receive operations or as a part of collective operations. And what we found is that there are many applications that are using GPUs that can tolerate some degree of data loss associated with compression. And this can have significant benefits at the very, very large message size. So we've had this for a little while, but it was kind of an all or nothing sort of design. You enabled compression for every all-to-all or all point-to-point operations, which can be a little bit difficult because even if your application can tolerate some data loss in some of the calculations, you may also have to do something like I/O that can't tolerate data loss. So we've recently moved to a new system for compression that we're hoping makes it a little bit more usable. This does unfortunately necessitate some minor changes in the application code, but we've moved this all into the MPI hints interface. So the hints that we use are listed up here in red for enabling with a given collective or for point-to-point or just for all collectives. But then we actually allow you to set that at each communicator. So you can set a communicator that does all of your compressible collective operations. You can set that at the beginning of your operation when you create your communicator, and then all of your compressible operations go through that communicator. and all of the ones that need to have 100% accurate data get to be preserved. So we're hoping that this will allow a lot more applications to take advantage of compression. And then that simplified the amount of work that you have to do with the CVAR interface. You can just essentially leave these as is and only deal with it in the hits. Yeah.
You have more than one communicator, each with a different type of compression?
Yes, you could have one communicator that is all-to-all compression enabled, one that's all reduced compression enabled. You could have one that has all-to-all and all reduced, and one that just has all-to-all. You can kind of customize those however you want. Same thing. These again mostly go away because you can just leave these set to per com, and then they'll only take effect when you enable them per com. You can still set them to all if you want to do the old all or nothing system, but we think this is going to be a lot more flexible. All right. Now, the last thing we're going to get into is kind of bringing this all together into a case study of how we look at actually optimizing performance on a real-life system, on a real-life application. So if there's one thing we really want you to take away from this is that mVAPITCH and mVAPITCH Plus are kind of like a nice sports car. It's going to go fast no matter who's driving, right? That's our intent. That's why we do things like the dynamic tuning. That's why we have all of these designs. But if you put a skilled and intelligent driver behind it, it's going to go a heck of a lot faster. Because if you know what you're doing and you take the time to learn the ins and outs of the mechanisms, you can really accelerate your applications because we've provided tunable parameters for all these things. And as an expert in whatever application you're running, or with a little bit of testing, you can really extract those last bits of performance that we're always looking for in high-performance computing. So, Ben, you want to start us out here?
So the point behind this is that most of our results, like half the results we have are micro benchmarks, and as I said, half the results, they're half the battle. In terms of these are just good for MPI collective evaluation in the case of in an isolated environment, very minimal realistic compute or communication pattern. But what happens if you want to go for any sort of benchmark, so that any sort of more lifelike benchmark or real world application? So over the summer, we had taken a look at high performance LIMPAC, largely through NVIDIA's release as there's optimized for CUDA GPUs, and thanks to help from Amit and others at TAC, we had tested a bunch of this on an NVL72 rack that they have as a sort of precursor to their upcoming Horizon cluster. More on that tomorrow from Dan. But so so there are many tuning points to broadcast. What algorithm do they use for, say, their internal collectives? What size n for their matrix do they use, etc. And basically, like, how do we go about fine tuning this? One thing to note one of the things that took a bit of time to get in that kind of frames a lot of the next couple of slides is LIMPAC is highly sensitive to broadcast. It is one of their main operations in terms of distributing parameters and intermittent updates. So there were over the course of like 2 solid months, like almost nonstop, and a consortium of us from the group that included Nat, myself, and myself, Sungjae and Gautam, and two from the lab, from other lab members, took apart these 7 or so, or 6 or so steps, and these were kind of applied in various orders. So one of the things is at what point, like, for HPL and any other specific application, these are the main bullet points, so to speak, and these kind of touch on a little bit of the flags that Nat and I had looked at earlier. So naturally, just to roll down the list, at what point do you want to switch between an eager and rendezvous message size? Certain applications dictate one protocol working out better for them than a different one. What kind of say broadcast or other collective algorithm do you want to use? This comes in conjunction sort of as a refinement from the dynamic tuning, where if you know your application well enough, you can say, okay, let's tune for specific broadcast, specific all reduced, etc. One of the things that mVAPITCH Plus and other MPI libraries have is this notion of what kind of GPU transport mechanism are you using? Are you using IPC mechanisms? Are you using staging between CPU, GPU, or are you doing some sort of hybrid? And this again is very architecture and cluster dependent. Another point from this, also boiling from the past several slides, is how do you want to place your processes? What transports work best for your application? RC, like for example, most people use RC, but at a certain scale, you get Q-pair explosion. What if you transfer to UD? Then your software and library have to do some level of message reordering at the transport layer library level, and so again, that may or may not benefit your application. That may or may not benefit like your scale execution, everything. At what point? Not every message size, for example, to go down the list again, may benefit from say using NVLink or Infinity Fabric, and that's again application specific. Most times the answer is you want to use it all the time. And then again, this all boils down to, is your application latency sensitive, bandwidth sensitive? In the case of LinPack, we're focusing more so on the bandwidth and say flops count versus how fast can we send our messages. Though most times the two of them go hand in hand. To see how this to showcase one point at the micro benchmark level, we were able to get up to 40% improvement at say 1K to 8 kilobyte range, and then up to a factor of 6 or a factor greater than 6 reduction at 4 megabyte messages.
And the important thing that we want to kind of point out with all of these things is that even though we're talking specifically about HPL and on these specific machines, these sort of questions come into play anytime you're optimizing an MPI library. And all of these features, we have default values that we think work in most cases, but by taking the time to go through and optimize these, that is how we are really able to extract that last bit of performance out of our systems, out of the Michalowicz library. And all of these are available, or the ability to adjust all of these is available in our user guide. And we would encourage you to take the time to experiment with them in your applications.
And if you have further questions, then you know where to find us. Yeah, and then so lastly, given the dense compute portion of HPL, and to see some experimentation, we compared a tuned Michalowicz Plus with many of the suggestions that we had taken on the previous couple of slides, and applied it here. Compared it to a couple of different mappings of OpenMPI. This one of the other main system installations on the NVL72 partition. We're at larger scale, so 16 nodes out of the 18 nodes, so 64 B200s. We're able to get 1.5% improvement of GFlop in terms of GFlops output. Now that doesn't sound like a lot, but given that the practical peak of 16 nodes of an NVL72 is around 2.07 teraflops, that does make a difference. And for those who are familiar with the top 500, that like 1.5% makes a huge difference in terms of a magnitude of like say 10 spots on the list. And this is just like the sort of beginning aspect. There are more enhancements to come after this as well.
And when you're spending several $100 million on a system, you want to get every ounce of performance that system is physically capable of providing. And that's what we're seeking to do. Yeah. So then just to kind of wrap things up here, in terms of future developments to watch out for. So we just made our OMB 8.0 release. We announced that we were working on this last year at MUG, and we're almost across the finish line. So this is a total refactoring of the OSU Microbenchmarks library. So we've cut down the file count a lot. We've made everything much more generic and easier to read and update. So the nice thing is we've had a lot of folks contribute patches back to OMB. We know a lot of people use that even outside the context of Michalowicz and are eager to contribute back. So this will make it a lot easier to contribute patches since you don't have to edit every single benchmark individually. You can do most of it in templated code, as well as some enhancements to the runtime that will allow you to do sort of full library tests or full system sweeps, similar to the IMB style of tests where you can just say, run all of my collectives and it will just loop over all of the collectives instead of having to run them each individually. Everything will still be backwards compatible, so if you have existing scripts that do all this already, we're not going to break those, but it does make life a lot easier when you want to run something very specific. And then as we move forward with the InvAppitch and InvAppitch Plus 5.x series and eventually 6.x whenever MPI 6 comes out, we are continuing to enhance our shared memory designs. Hopefully bringing some of those enhancements alongside the UCX netmod so that we can get a little bit better performance there. Continuing to enhance our GPU collectives. We've done a lot of work on that in the past year, bringing more kernel-based algorithms and more enhanced collectives than we've had before, as well as integrating GPU-initiated communication from your CUDA or HIP kernels. And Dr. Penn is going to talk a little bit more about that later. And then funding acknowledgements. Thank you to all of you here and all of you who are joining us remotely, as well as everyone who's supported us in the past, as well as all of our current and former students. Any questions? We've got a little bit of time. Yes. Can you use the microphone, please?
Can you go to the the memory copy?
Yes.
Async. And so you have said that it picks the best one. So have you seen any instances where it doesn't use async?
Oh, instead of CUDA copy async?
Yeah.
Yes, there's a lot of times where that may not be necessarily the best method for what we're achieving here. So that is a good example of something that you might do to essentially accomplish what we were describing here, right? Where you are doing this sort of pipeline design, but you also have a lot of systems now that have GPU direct RDMA. So there may be no need to even involve the CPU at all. We might be able to just go directly from the GPU through the NIC to the other GPU. So that would be an example of a time you don't want to do that. For very, very small messages, just like with pipelining in general, sometimes it's not worth it to pipeline. The overhead of breaking up the message is just not worth it. So you may want to just do a simple CUDA mem, or well, you wouldn't do a CUDA mem copy, but you can do a simple one-step copy without pipelining. Any other questions? Yeah.
Thanks for the talk. I know that Professor Panda may share more about the GPU-initiated communication, but as you're all looking at it right now, do you see any standardization there? Because it's focused to a certain vendor. When we, as an XPU vendor, try to build some of the features, that's a bigger black box for us. How do you all looking at it from the research point of view?
So it kind of breaks down to a couple spots. So we are on the one hand for vendors, we are trying to keep a pulse, as a research MPI library, we are trying to keep a pulse on what other vendors are doing. So not just DMatrix, for example, but also what is AMD doing, for example, with their own like say GPU direct async things and kernel and GPU initiated communication. As well as reaching out to other friends in industry that may be here, may not be here. From the MPI standard perspective, the folks in the standard are also working on the notion for MPI plus GPU initiated communication. So it's standardized. So it's also its own standardized aspect. So it kind of comes from both sides. You have to have there's a standardized approach to it that's trying to be brought up in the MPI standard. And then it's also seeing how that interacts with hardware, so that way you don't have to face constraints when designing like a large scale application. Does that answer your question?
It does, yeah. I'll follow up offline too. Thank you.
Awesome.
Any other questions? All right, thank you very much.
Okay, so we'll go to the final session of today's. We